Okay. Okay, so let's start then. Last time we were talking about derivatives of maps between Euclidean spaces and between normed vector spaces. And then we talked about higher derivatives, right? So the higher derivatives were the kth derivative at a point was, we saw it was a symmetric multilinear map, right? K multilinear map. And let me just see. Right. So this K multilinear map, the kth derivative, acting on the diagonal v comma v comma v k times, where v is a vector in the domain. This was just the kth derivative of the map f along the straight line passing through P in the direction of V, right? Okay. And we also saw that for a symmetric multilinear map, the values of the multilinear map are determined by its values along the diagonal, right? If you vanish along the diagonal for all V, then you vanish identically on all k tuples of vectors v1 to vk, right? We saw this as well. And then we had the Taylor theorem. So we could write f near a point x as a sum of the derivatives evaluated along the diagonal plus an error term. So if you were k times differentiable, ck, then the error term was little o of norm h to the k. Okay. And so then we talked about the second derivative. So the second derivative is a symmetric bilinear function. If f is a map from Rn to R, a C2 function, then the second derivative is a symmetric bilinear function. So a symmetric bilinear form, we know Rn is a inner product space. So in an inner product space, a symmetric bilinear form is can be identified with a self-adjoint linear map, or in other words, a symmetric matrix. So the second derivative could be identified with a symmetric matrix such that d squared f of v comma w is the inner product of hv comma w, right? Where H is the symmetric matrix associated to the symmetric bilinear form. And it's just this matrix H was the matrix of second order partial derivatives, del squared f, del xi, del xj. So this is called the Hessian matrix of f. Okay. So if you like, this arises from the identification when you have an inner product space between symmetric bilinear forms and self-adjoint linear maps. Okay. And then we saw that the second derivative test, it generalizes to higher dimensions. So if f from Rn to R is a C2 function, and we take a point P in U in the domain of f. So if P is a local maximum of f, then this Hessian matrix is negative semi-definite. Okay. And if converse, if the derivative is 0 at a point, the first derivative, and if the Hessian is strictly negative definite, then the point P is a local maximum of f, a strict local maximum, right? So the proofs of these were straightforward. For the first part, if P is a local maximum, then you look at the straight lines P plus TV passing through P. So F restricted to each straight line is just a map from R to R, which has a local maximum at t equal to 0 and is twice differentiable. So its second derivative has to be less than or equal to 0. So 0 is greater than or equal to d squared dt squared at t equal to 0 of f of p plus tv. This we know is the same as d squared f at p of v comma v, which is the same as inner product hfpv comma v. So therefore the Hessian is, this is true for all vectors v. So the Hessian is negative semi-definite. And conversely, if the Hessian is negative definite, then that means the associated quadratic form restricted to the unit sphere is negative everywhere. Therefore, its supremum, if I call it epsilon naught, this is strictly negative. And so then if I use Taylor's theorem up to second order, f of p plus h is f of p plus there's a first order term dfp of h, but we're assuming the first derivative is 0. So the first order term vanishes. Then we have a second order term. So that is the second derivative 1 over 2 factorial d squared fp of h comma h. That's the same as 1 over 2 factorial inner product hfp h comma h plus a term which is little o of norm h squared. And here this hfp of h comma h, this is homogeneous of degree 2 in h, right? So this is going to be norm h squared into the value of this quadratic form at a point on the unit sphere. And on the unit sphere, this is less than or equal to epsilon naught, which is strictly negative. So this second order term is less than or equal to half epsilon naught norm h squared plus a term which is little o of norm h squared. So here epsilon naught is fixed. So as h tends to 0, this term which is little o of norm h squared, this plus half epsilon naught norm h squared will be less than 0, right? And so the whole thing will be strictly less than fp when h is small and non-zero. Is this okay?
Yes, sir.
Okay, so therefore f has a strict local maximum if the Hessian is strictly negative definite. All right, so we were talking about, we started by talking about derivatives. So let's calculate the derivative of one very important function for us, which will be the determinant. So the determinant I can think of as a function from the vector space of n by n real matrices, M and R, to R, right? And I can also think of this as a multilinear function of n column vectors, right? It's multilinear in the columns of the matrix, right? So I can also think of it as a multilinear function. So what is the derivative of this determinant? So first, let's compute the derivative of the determinant at the identity. So suppose H is a square matrix with columns H1 to Hn. So then note that the norm of each column, Hi, this is the same as the norm of H times Ei. And by definition, this is less than or equal to norm H into norm Ei. Norm Ei is 1. So this norm of Hei is less than or equal to norm H, right? By definition. And therefore, if I look at the determinant of a matrix where k of the columns are columns of H and the others are the basis vectors E1 to En, I've just replaced k of these columns by columns of H. So Hi1, Hi2 up to Hik. Then this is a multilinear map, the determinant. So this is less than or equal to the norm of the determinant as a multilinear map into the norm of E1, norm E2, up to norm HI1, norm HIK, norm EN. So the norms of the EIs are 1. The norms of the HIJs are less than or equal to norm H. So the whole thing is less than the norm of the determinant into norm of H power K. Okay. So now if I look at the determinant of identity plus H, I want to calculate the derivative of the determinant at the identity. So I need to look at a small perturbation of the identity. So let's look at the determinant of I plus H, where H is a matrix whose norm is small. So I write this as determinant of E1 plus H1 up to En plus Hn, right? Now I use the multilinearity and I expand this. By multilinearity, I can expand, right? I'm going to get 2 power n terms, right? So in each spot here, I have to choose either an EI or an HI. So there are going to be 2 power n terms. But out of those terms, the first term is going to be where I choose all the EIs and there are no HIs. So that gives me determinant of E1 to En. Plus, then there are going to be n terms where I have exactly one Hj and the others are EIs. Okay, so that will give me a sum over j, determinant of E1 up to, so there's a typo here, this should be Ej minus 1, and then Hj, and then Ej plus 1, and then up to En. Okay, so there's a typo, I'm sorry, this should be Ej minus 1 and Ej plus 1. So in the jth spot, I've got Hj instead of Ej. And then I'll get other terms where there are at least 2 H's. So by this above estimate here, whenever there are 2 H's, I get a term which is big O of norm H squared or higher, right? So the whole thing, all the other terms will give me something which is big O of norm H squared. Yes? Okay. Yeah. Yes. So these higher terms will be basically, they will be polynomial functions of H of degrees at least 2 or higher. Okay. This first term is linear in H, you see. This first term is linear in H. The other terms will all be polynomials of degree 2 or higher in H. So those will be big O of norm H squared. So when I'm calculating derivatives, I can ignore that higher order term. So now I just look at the linear term. And then the linear term, again, what I can do is Hj, I write as a sum over I, Hij, Ei. And I substitute that here. Then I use the multilinearity of the determinant. So this sum over Hij, Ei, the Hij will come out as a sum over I. And then I will have Ei here. Okay. So, well, this typo is making it hard to understand. Let me just write it here. So what we have is, I'll just do the calculation without the typos. So we have H is, what's going on? Yeah, so H is H1 to Hn, and then determinant of I plus H. So this turns out to be, so there's a 0th order term, determinant I. Then there's a first order term, sum over j, determinant of E1, Ej minus 1, Hj So this should be Ej plus 1, En, and then big O of norm H squared. And so then this next term is a sum over J, determinant of E1 to Ej minus 1, sum over I, Hij Ei, Ej plus 1, En plus big O of norm H squared. And now I use the multilinearity. So this is determinant of identity plus sum over J, sum over I, Hij, determinant of E1, Ej minus 1, Ei, Ej plus 1, En plus big O of norm H squared. And so what happens in this determinant? As you sum over I, what happens? Well, if I is not equal to J, then EI will be repeated twice, right, in this determinant? Yes. And so the determinant will be 0, right, if I is not equal to J, right? Because then the column EI will occur twice. So the only term which will remain is when I is equal to J, right? So therefore, this will become determinant I plus sum over J, Hj. So I has to equal J. So this is Hjj. And then determinant when I is equal to J, this is just the identity matrix. So this is just 1, right? Plus big O of norm H squared. Okay, so finally we get this is equal to determinant I plus this sum over J, Hjj is nothing but trace of H plus big O of norm H squared. Okay, is this all right? So this trace H, this is linear in H. And this big O of norm H squared, this is my error term, E of H, in the definition of differentiability. And this is little o of norm H. Okay. So therefore, by definition, det is differentiable at the identity in M and R, and the derivative of the determinant at the identity. So this is going to be a linear map from M and R to R. This is just the trace. H goes to trace of H. Is this okay?
Yes.
Okay. And once we have the derivative at the identity, then using the fact that, well, GLNR is a group, right, which acts on itself by translations, and determinant is a homomorphism from GLNR to R minus 0. It's a homomorphism. So using that, it's easy to calculate the derivative of the determinant at any invertible matrix. So if A belongs to GL and R, and H now is in M and R, so then so then what can I do? So determinant of A plus H, I can write as determinant of A times identity plus A inverse H. And so this, since the determinant is multiplicative, this is determinant A into determinant identity plus A inverse H. Okay. And now note that norm of A inverse H by the properties of the operator norm, this is less than or equal to norm A inverse into norm H. So this tends to 0. Well, so this is a big O of norm H. So it tends to 0 as H tends to 0. So this, as H tends to 0, A inverse H is small. So since the determinant is differentiable near the identity, this determinant of identity plus A inverse H, I can write as 1 plus trace of A inverse H plus little o of norm A inverse H. Right? Using the differentiability of the derivative at the identity and the fact that the derivative at the identity is the trace, I can write this when H tends to 0. So then I multiply by determinant A. So what I get is determinant A plus, so I get determinant A times this trace. So let me take the determinant inside the trace. Then I get trace of determinant A into A inverse, right? And then into H. And then plus, well, norm of A inverse H, this is big O of norm H. And little o of this will therefore be a little o of norm H, right? Is this okay?
Yes.
So now this middle term, this is linear in H, and the error term is little o of norm H. So this will be the derivative, right? But this we can write in a different form. What is determinant A into A inverse?
Adjugate of it.
Is the adjugate, right? Or the transpose of the adjugate, right? I think it's the transpose of the adjugate.
This is the transpose.
Right, because in the inverse, you have a transpose of the cofactor matrix, right? So,
yes.
Yeah, right. So this is A adjugate transpose into H. So, well, there's an error in the notes. I've written the adjugate matrix in this computation, but it should be the transpose, I think. It should be the transpose. Yeah, okay. So anyway, so this implies that determinant is differentiable at A and the derivative of the determinant at A applied to H is this linear function of H. It's the trace of A adjugate transpose H. Okay. Now, the point is, this is for A in GL and R. And H in M and R. But the derivative is a polynomial function, right? Derivative is just a, derivative, I'm saying the determinant. The determinant is just a polynomial function, right? So its derivative will also be polynomial. Each component of the derivative will also be a polynomial function, right? In A and in H. So, and similarly, the right-hand side is also a polynomial in A and H, okay? And so both sides are polynomial functions, and this is true for all A and GL and R, but GL and R is dense in M and R, right? Yes?
Yes.
So therefore, by continuity, since both sides are polynomial functions, this is true for all A and M and R, right? And thus, also for all A in M and R by continuity of both sides in A, H, and density of GL and R in M and R. Okay, is this all right? So this finishes the computation of the derivative of the determinant. And see, the one thing I would like to say is that, yes, we know that for a map between Euclidean spaces, the determinant I can write in terms of the Jacobian matrix, right? Del Fi, del Xj, and so on. Or if it's a function from a vector space to R, I mean, from Rn to R, then in terms of the partial derivatives, del F, del Xj. But in this case, I mean, it would be meaningless to compute the partial derivatives of the determinant, right? That gives you no information about what the derivative actually is. It's clear here that it's better to see the derivative as a linear map rather than a collection of partial derivatives, right? When you see it as a linear map, you get this nice, clean formula for the derivative, okay? So even in finite dimensions, it's often better to think of the derivative as an abstract linear map rather than a matrix, right? Is that clear?
Yes, sir.
Right. So, yeah. Okay. So fine. So this calculation will be important for us later when we talk about the Laplacian. Because, well, I mean, the determinant essentially is related to volume, right? It's a signed volume. And so the derivative of the determinant means the change in volume under small perturbations. The change in volume is the trace. I mean, actually in simple examples, that's easy to see. You see, the derivative of the determinant will be the trace, because if you think of it as volume, then, you take at the identity that corresponds to a square, let's say, and then what is the change in the volume in the area? Well, I'm adding a small hi here and an h1 and an h2 here. So if this is, say, h1 and this is h2, okay, and this is e1 and e2, right? So this this area is h1 into 1, and this area is h2 into 1, sorry. And this area is h1, h2. This is big O of norm h squared, right? Okay. So here what I'm doing is I'm calculating the derivative of I'm calculating the change in determinant under when I restrict myself to diagonal matrices, right? So in this case, it's just a 2 by 2. So let me just write that, a 2 by 2 matrix. E1 plus H1 and then E2 plus H2. Right, so this area or this determinant is just, it's 1 plus H1 plus H2 plus big O of norm H squared. And you see this is the trace, right? Is it clear? Yeah.
Yes.
Right. So, I mean, the same will be true in higher dimensions, in higher dimensions. You can see that the derivative of the determinant will be the trace. So you'll take a cube, the unit cube, and then, well, you'll have an H here and so on. And so. I'm not sure if I'm drawing this correctly. Okay, well, I've made a mess of it. Anyway, sorry. So, well, you'll see that, you'll get the terms, the main contributions, the linear terms will have one H, let's say an H2 here and two EIs. And so you'll get H1 plus H2 plus H3. And the other terms will have at least two H's. So those will be big O of H squared, norm H squared, right? Okay, you see the picture?
Yes.
In higher dimension, it's quite clear. Okay, so the derivative of the determinant is the trace at the identity. At the identity, it's just the trace. Okay, so now, yeah. So we've talked about the determinant. So the determinant is is a multilinear function of its columns, right? And it also gives you a notion of volume, right? So if so if I have two vectors, say in R2, V and W, so this determinant of VW, what is this? This is the signed area of the parallelogram, right? Spanned by VW. So this is positive if, so I look at the anti-clockwise angle from V to W. So this determinant will be positive if theta is less than pi, right? And negative if this angle theta is bigger than pi, right? Yes?
Yes.
Right. Now, looking at these two cases where the angle is less than pi and bigger than pi, this will actually lead us to the concept of what is called orientation on a finite dimensional vector space. And so I'll talk about that in a bit. This meeting is going to end in 2 minutes. So briefly, I'll just say now, see, orientation will be, well, geometrically, what it corresponds to is, you see, if I look at the set of ordered bases of a vector space, right? So let me call that, say, B of V. So V is a finite dimensional vector space. So say if I look at B of V, so this is the set of all V1 to Vn in V power n, such that V1 to Vn is a basis of V. Okay. So this is the set of all ordered bases of V. So, well, I'm going to talk about this. Let's stop this meeting. There's less than 1 minute and we'll start a new meeting. Okay, so I'm stopping this now. Okay. Right. So, right. So what I was saying is, in R2, see, we have these two cases where the determinant is positive and negative, right? This corresponds to two different types of ordered bases, right? Either the ordered basis, the angle is less than pi, or the angle, the anti-clockwise angle between them is bigger than pi, right? And actually what this corresponds to is the following. you look at the set of all ordered bases, B of V, right? So this is the set of ordered n tuples V1 to Vn in V power n, such that the set V1 to Vn is a basis of V. But here the ordering of the basis is important. Okay, the ordering is important. So this has a natural topology, right? This space. So this is just the subspace topology from sitting inside V power n. Okay, right? So this has subspace topology. And in fact, it's an open subset of V power n, right? It's just an open subset in V power n. Because I mean, the determinant of, if I write this as column vectors, the determinant is a continuous function, right? So if the determinant of V1 to Vn is non-zero, then nearby close to this, for all n tuples close to V1 to Vn, the determinant will be non-zero. So it will stay a basis, right? So this is an open subset of V power n. And also I have an action of GLV, right? The invertible linear maps of V. GLV acts on this set of ordered bases, right? The action is just G dot V1 to Vn is GV1 up to GVN, right? Okay. This action is what's called simply transitive. So that means it's transitive, and given any two elements in my set B of V, there is a unique G in GLV which takes the first n tuple to the second n tuple, right? That's clear because, I mean, given any two ordered bases, there's a unique linear map which takes the first ordered basis to the second ordered basis, right?
Yes.
So what this means is, so if we fix so if we fix an ordered basis E1 to En in B of V, then I get a map phi from GLV to B of V, G goes to GE1 up to GEN. This map is, because the action is simply transitive, this map is onto and one-to-one, right? Yes? And it's easy to see it's continuous and the inverse is continuous. Therefore, this map is a homeomorphism. Okay? Is this clear?
Yes.
Now, what is an orientation? Well, an orientation, you can see it in this picture. In R2, for example, the set of ordered bases where the angle is less than pi and the set of bases where the angle is bigger than pi, these are nothing but the two connected components of B of V of the set of ordered bases. Right? If I have any two ordered bases where the angle is less than pi, then I can join one to the other, right? I can deform this basis into this basis, right? First, I I just rotate this vector and I scale it so it becomes the first vector. And then I can rotate the second vector, keeping the first one fixed, right? Until it becomes the second vector, right? I can do this because both the angles are less than pi. So when I rotate this second vector to become this second vector, I will never pass through. So if this is v, I will never pass through minus v, right? So throughout the deformation, my two vectors will stay linearly independent. Is this clear? Yes?
Yes.
So any two where the angle is less than pi, this will form one connected component of B of V. Similarly, any two where the angle is bigger than pi will form another connected component of B of V. Okay? And these are the only two connected components, right? Okay? I mean, these two cannot be connected, right? If I have to go from angle less than pi to angle bigger than pi, I mean, just intuitively, what you can see is somewhere in the middle, the angle has to equal pi, and that will be a contradiction, right? It won't be, the two vectors won't be linearly independent, right? Well, if you want to direct an actual proof, you just look at the determinant function. It's positive on this connected component and negative on this. So, I mean, well, so these can't be connected, right? If they were connected, then somewhere in between the determinant would have to be 0 by the intermediate value theorem. And so that cannot be possible, right? So these are the two connected components of B of V. This you can see in 2 dimensions. It's just angle less than pi, angle bigger than pi. But in higher dimensions, it's also true, right? So B of V will also have just 2 connected components in higher dimensions as well. Those will be the same, the 2 connected components of GLV, right? So connected components of the set of ordered bases B of V. This is in correspondence with, because these spaces are homeomorphic, this is in one-to-one correspondence with connected components of GLV, and the 2 connected components are GL plus of V, linear maps with positive determinant, and GL minus of V, linear maps with negative determinant, right? Okay, so you can try and prove this, that GLN R has exactly 2 connected components, the matrices with positive determinant and with negative determinant, right? These are the 2 connected components of GLN R. Yeah, can you show that?
Yes.
Okay, you can use, for example, the Cartan decomposition, right? K. Or even the Iwasawa would do it, I think. Yeah. Yeah.
Yes.
Right. Yeah. So, yeah. Okay. All right. So, so an orientation actually is an orientation on a vector space is going to correspond to a choice of one of these 2 connected components. An orientation on a vector space, a finite dimensional vector space V, is nothing but a choice of one of the 2 connected components of the set of ordered bases. All right. Yeah. So that's what an orientation will be. So 2 bases give the same orientation means that you can deform one ordered basis continuously into the other. Right? That's what it means. I mean, the connected subset of open connected subset of a vector space. So it is path connected, right? So the connected components are path connected. So that just means that in each connected component, I can deform any ordered basis into any other ordered basis in the same connected component. And so then I'll say that they give the same orientation. So anyway, I'll give the definition a bit later. Now let's talk about what are called alternating forms. So we saw that the higher derivatives were symmetric multilinear maps, right? So those are in elements of V tensor power k, which are invariant under permutations of the vectors by elements of Sk. Now we are going to talk about multilinear maps which are close to the determinant. So the determinant is alternating. That means if I interchange two columns, then the determinant changes sign, right? So similarly, now in general, I'm going to say that a k-tensor alpha, so that means a k multilinear function from v cross v cross v k times to r, is alternating if when I interchange two vectors, then alpha changes sign. Okay. So alpha of v1 to vi vj up to vk is minus of alpha of v1 to vj vi vk. Okay. And so if you change sign under one transposition, then that means under a general permutation, you're going to change sign by the sign of the permutation, right? So alpha of v sigma 1 to v sigma k will be sine sigma into alpha of v1 to vk for all sigma and sk. Is this clear? Yes?
Yes, sir.
Okay. All right. So the basic example of an is the determinant. So if so suppose the dimension of v is n, then the determinant, this is a n multilinear function on v. This is an alternating tensor. All right. Okay. So in general, we're going to define wedge k of v star. This is going to be the vector space of alternating k tensors. Okay. So alpha in v dual tensor k such that alpha is alternating. So note that this is a subspace of the space of k tensors. Okay. So there's just a little point of linear algebra to mention here. Normally, the kth wedge of a vector space is defined as a quotient of the kth tensor. Okay, it's not a subspace. Normally, it's defined as a quotient. But in the case where I'm looking at the kth wedge of a dual space of V star, then this can naturally be identified with a subspace of the kth tensor of V star. Okay, so just a little bit of linear algebra to, I mean, you can look at Hoffman and Kunz. I
Can you
think they have the
repeat
abstract.
what last thing you said? That how can we just?
Sorry?
Can you just repeat what you said? When how can we identify it as a subspace?
Yeah. So see, normally what happens, let me just write this here. So normally, you see V tensor power k, right? This is a, how do I say this?
By
This is
the abstract definition of tensor, this is some quotient. Yeah.
Well, I mean, this is basically you take the free vector space on the symbols V1 tensor, V2 tensor, V3 tensor, V4 tensor, V5 tensor, V6 tensor, V7 tensor, V8 tensor, V9 tensor, V10 tensor, V11 tensor, V12 tensor, V13 tensor, V14 tensor, V15 tensor, V16 tensor, V17 tensor, V18 tensor, V19 tensor, V20 tensor, V21 tensor, V22 tensor, V23 tensor, V24 tensor, V25 tensor, V26 tensor, V27 tensor, V28 tensor, V29 tensor, V30 tensor, V31 tensor, V32 tensor, V33 tensor, V34 tensor, V35 tensor, V36 tensor, V37 tensor, V38 tensor, V39 tensor, V40 tensor, V41 tensor, V42 tensor, V43 tensor, V44 tensor, V45 tensor, V46 tensor, V47 tensor, V48 tensor, V49 tensor, V50 tensor, V51 tensor, V52 tensor, V53 tensor, V54 tensor, V55 tensor Vk, V1 to Vk in V. And then you quotient by the natural, multilinearity relations, right?
Yes.
So the relations will be of the form, whatever, V plus W tensor, V2 tensor, Vk. So you have to take this minus V tensor Vk minus W tensor V2 tensor Vk. Right? That means I look at the subspace spanned by such vectors and I quotient by this subspace, right?
Yes.
I have to do this for each index. I goes from 1 to k.
Yes.
Right? I quotient by all these relations. Okay, so that will give you just the tensor product, right?
And also R times V, that one we need, right?
Right. But the scalars also, yeah, the scalars. So alpha V tensor. I'm not writing everything down. It's a bit long. So
Yeah.
you understand, right?
Yes. Yes.
This minus alpha into V tensor, etc.
Yes.
Okay, fine. Right. So anyway, so you get this is the tensor product. And normally the wedge, the kth wedge of V is equal to the tensor product quotiented by some relation. So it's just the relations that if I interchange any two, they should
A sign should appear that those solutions.
yeah. So I mean, so something like say V1 tensor V2 tensor Vk in the wedge, this plus V2 tensor V1 tensor Vk, this should be 0, right?
Yes.
Okay, so you'll quotient by these sort of sums. Is it clear?
Yes. Yes.
Yes, sir. Yes.
So the wedge is normally a quotient of the tensor product. Okay, but in the special case where instead of V, if I'm looking at a dual space, right? So then V dual tensor power k. This is a natural isomorphism. This is a canonical isomorphism. Means you don't have to choose bases. This is canonically identified with multilinear maps from V to R. Right?
Yes.
Okay, there's a canonical isomorphism here. And wedge k of V star, this is canonically identified as a subspace of again MKVR, the subspace of alternating tensors. Is this clear? So
Yes.
that's what I'm saying. Okay. All right.
Yes.
Okay. So yeah. So I mean, just to remind you that normally the wedge is actually a quotient, but in this case, it's becoming a subspace. When we're looking at the wedge of a dual space of V star, when we're looking at the wedge of V star, it becomes a dual space. It becomes a subspace of the space of multilinear functions. Okay. Anyway, that's just some linear algebra. For our purposes, we'll only look at alternating tensors. Right? Here, a tensor means a multilinear function. Okay, when I say tensor, I mean a multilinear function. Okay, so now how do we construct alternating tensors, right? So, so this is a very simple thing. You see, we have this, well, there are two actions actually. Of the symmetric group on V star tensor K. So this, which is I'm thinking of as the multilinear functions MK VR. So one is the standard action. So sigma dot alpha of V1 to Vk is just alpha of V sigma 1 V sigma k. Right, this is the standard action. Okay, so for this standard action, sigma dot alpha is equal to alpha for all sigma if and only if sigma is a symmetric tensor, right? Yes, that's the definition of what a symmetric tensor is.
Yes.
So alpha belongs to sim k V star. This is a subspace of V star tensor power k. Okay. Now we have actually, so I mean, so how will you construct something which is invariant under the whole group? What's the obvious thing to do?
Average it out.
Just average it out, right? So you can have a projection map, right? P from V star tensor k to sim k V star alpha goes to 1 over k factorial sum over sigma in sk sigma dot alpha. So this will give you, for every k tensor alpha, this will give you a symmetric k tensor, right? Okay, and this will be a linear map and it's a projection, right? If I apply this to something which is already symmetric, then this will give me the, I mean, it will give me back the same tensor. So this will be a projection, right? P squared is equal to P, right?
Yes.
Okay. Now the point is, the symmetric group has, well, two homomorphisms to Z2. There's the trivial homomorphism and there's the sign, right? The sign homomorphism. So what happens is, because you have the sign homomorphism, taking values in, you know, -1, 1, you can define another action. Well, I should have used some other notation, but anyway, I'll just use the same notation. So in this case, the action is sigma dot alpha acting on V1 to Vk. This will be sine sigma into alpha of V sigma 1 V sigma k. Okay, so this is a twisted action. I'm twisting by this homomorphism sign, right? Yes?
Yes.
So with respect to this twisted action, sigma dot alpha is equal to alpha for all sigma, if and only if what? Alpha must be an alternating tensor.
Tensor.
Right? So alpha belongs to wedge k v star. Right. So if I want to construct alternating tensors, then what I should do is just do what I did in the previous example, average, but with respect to this action, the twisted action, not the standard action, right? So that leads us to the definition of a similar projection for the alternating tensors. So the projection is called the alt map. So alt goes from V dual tensor K to wedge K V star. Alpha goes to 1 over K factorial sum over sigma in SK. So sigma dot alpha, maybe I should put a tilde over the dot to say it's a twisted action, okay? So it's a twisted action. So alpha dot tilde, I mean, yeah, sigma dot tilde alpha, right? Is this clear?
Yes.
Okay, so this will be a projection in the sense that alt squared will be equal to alt, right? Yeah, so if I start with an alternating tensor, I'll just get back the same alternating tensor, right? Okay.
Yes.
All right. So this gives us a way to construct alternating tensors. And this leads to what's called the wedge product between alternating tensors, which is defined as follows. So suppose alpha is a k-tensor, an alternating k-tensor, and beta is an alternating L-tensor. Then the wedge product of alpha and beta, this is defined to be a k plus L alternating tensor. So how do I do that? So first what I do is I take alpha tensor beta, all right? So alpha and beta are tensors, so I can take their tensor product. The problem is the tensor product will not be alternating, right? In general, the tensor product of alternating tensors will not be alternating. So then what I do is I apply alt to it, right? I apply alt to this. So then alt of alpha tensor beta will be an alternating tensor. This is good. Now the only thing is I need to put in some constants in order to make this wedge product associative, all right? So it turns out the right thing to put is k plus L factorial divided by k factorial L factorial, okay? So this is the definition of the wedge product. Is it clear? So this is a k plus L alternating tensor, okay? All right. And then you can show, I won't do this, but it's not hard to show. The wedge product is associative. And we can give a formula for the wedge product of 3 alternating tensors. So omega wedge eta, the whole thing wedge theta, is the same as omega wedge in brackets eta wedge theta. And this I can write as k plus L plus n factorial divided by k factorial L factorial n factorial into alt of omega tensor eta tensor theta. Okay. So I won't prove this, but yeah. So this is a fact. So now once we have this formula, by induction, I can write down a formula for the wedge product of n forms, say alpha 1 to alpha m. Okay. It is going to be the following. Alpha 1 wedge up to alpha m. This wedge product of m forms is going to be k1 plus dot 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 plus km, the whole thing factorial, divided by k1 factorial up to km factorial into alt of alpha 1 tensor up to alpha m, where here each alpha I is a ki form. That means it's a alternating form of degree ki. Okay. Is this clear? So
Yeah.
I'm not proving these. I'm just stating this formula. I'm not going to prove them. But now we can use them to understand this wedge product in terms of determinants. So what happens if I take a wedge product of k1 forms? So when I say one form, what I mean is just linear functionals, right? So I can take the wedge product of these, k of them. That's going to be a k form, right? It's going to be alternating of degree k. So what is alpha 1 wedge alpha k acting on vectors v1 to vk? So by this formula above, this is going to be 1 plus 1 plus 1 k times the whole thing factorial divided by 1 factorial up to 1 factorial. So this is going to give me k factorial into, then I have alt of alpha 1 tensor alpha k, the whole thing applied to v1 to vk, right? Now, what is alt of this applied to v1 to vk? So remember, in alt, it's an average. So there's a 1 over k factorial in alt, right? So that 1 over k factorial will cancel with this k factorial here. And then I'll just get a sum over the symmetric group, sum over sigma in sk. So then I will have sine of sigma, and then I will have alpha 1 tensor alpha k applied to v sigma 1 to v sigma k. So that's going to be alpha 1 of v sigma 1 into dot 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 alpha k of v sigma k, right? Yes?
Yes, sir.
Now, what is this? This I recognize as the determinant of a k by k matrix, right? Just the definition of determinant in terms of a sum over the symmetric group, right? This is a determinant, yes?
Yes, sir.
So it's the determinant of this matrix where each column is basically the image of the vector v1 under alpha 1 to alpha k, right? You see, if I have alpha 1 to alpha k in v star, this defines a linear map T from V to RK, little v goes to the column vector alpha 1 of V up to alpha k of V. Right? And then alpha 1 wedge alpha k of V1 to Vk is nothing but the determinant of the matrix with columns TV1 up to TVK. Is this clear?
Yes.
Yes. Yes.
So it's this determinant. Okay. Now we can see then, in particular, if E1 to En is a basis of V, and E1 star up to En star is the dual basis of V star, then what will be E1 star wedge up to En star? In that case, this matrix will just become the identity, right? Sorry, I mean, this linear map, this where the alpha i's are just the EI stars, right? That will be just the expression of the vector V1 in terms of the basis E1 to En, right?
Yes, sir.
Yes?
Yes, yes.
Right?
Yes.
So then this determinant will be just the determinant of the matrix with columns V1 to Vk, right? So that means this alpha E1 star wedge En star is just equal to the determinant, right? In this case, yes?
Yes.
Right. Yes.
Where the determinant I think of as an element of wedge and V star, all right? The determinant is an element of wedge and V star. Okay, fine. Now from this, writing this wedge as a determinant, we get other properties also. So alpha 1 to alpha k are in V star, and sigma is in Sk, right? Then okay, so then what happens if I permute the alpha i's? So if I permute the alpha i's, this this square matrix, okay. So if I permute the alpha i's here in this wedge product, then the columns, the rows of this matrix will get permuted, right? So therefore the determinant will change by a sign of sigma, right? So that means alpha sigma 1 wedge alpha sigma k is sine sigma into alpha 1 wedge alpha k, right? Where the alpha k's are, the alpha i's are one forms, okay? Yeah, so the wedge product is also alternating, applied to one forms. The wedge product is alternating. And using this, I can also see that if I take k basis vectors, the duals of k basis vectors, ei1 star up to eik star, where i1s are strictly increasing, I1 less than I2, strictly less than IK, less than or equal to N. And now if I take another strictly increasing K tuple, J1 up to JK, then EI1 star wedge EIK star, this applied to EJ1 to EJK, this will be 1 if and only if I1 to IK is equal to J1 to JK. So, yeah. Okay. All right. Yeah. So we're looking at the wedge product of one forms. So if I take I1 to IK in strictly increasing order and also J1 to JK in increasing order, then EI1 star wedge up to EIK star applied to EJ1 to EJK. I'm saying this will be 1 if and only if I1 to IK is J1 to JK and 0 otherwise. So how do we see this? We can write this as the determinant of a square matrix, a K by K matrix. So look at this J1, right? So if J1 is, what is the argument? Yeah. So if J1 is bigger than I1, right? Then
So can you speak a bit loudly?
Oh, sorry. Yeah. So I'm saying I want to show this, right? this wedge product applied to this k basis vectors is either 1 if the two multi-indexes are the same, or 0. So why is that? Because if suppose J1 is strictly bigger than I1, right? Then all the J's will be bigger than I1. So that means this first row will become 0, right? Yes?
Yes, sir. Yes.
Yes.
So J1 has to be less than or equal to I1. But now if J1 is strictly less than I1, right, then this first column will become 0, right? Yeah, because all of the i's will be bigger than J1. So all of this whole column will become 0, right?
Yes.
Yes, sir.
Okay, so therefore J1 has to equal I1. All right. So then the first column will become, the first row will become 1, 0, 0, and the first column will become 1, 0, 0, right? When J1 is equal to I1. And then after that, similarly, you can argue that J2 has to equal I2 and so on. Is it clear?
Yes, sir.
Yes.
Yeah.
Sir.
Okay, that's it. So therefore, you'll get that if, yeah, this is, if it's non-zero, then, I mean, J1 to Jk has to equal I1 to Ik. And then this determinant is 1. Otherwise, it's 0. Okay. So using this, we can then write for any alternating k-tensor alpha, I can write it as a linear combination over multi-indices I1 to Ik in strictly increasing order of these basic wedge products, EI1 star wedge EIK star, into alpha of EI1 to EIK. Okay, so I claim that we have this representation. So why is this true? Because the left-hand side and right-hand side are both alternating k-tensors. And to show that they are equal, it suffices to show that they are equal on k-tuples of basis vectors by multilinearity, right? But since they're alternating, both are alternating, it's enough to show that they're equal when applied to basis vectors arranged in increasing order, right? Because they're alternating, right? So it's enough to look at k-tuples of basis vectors in increasing order, right? Since any k-tuple of basis vectors, I can permute to arrange them in increasing order. Okay? And so if I take a k-tuple ej1 to ejk and I apply both sides to it, then on the left-hand side, I'll get alpha of ej1 to ejk. And on the right-hand side also, by this property above, all the terms here, when I sum over I1 to Ik, will be 0, except when I1 to Ik is equal to J1 to Jk. And then I'll get 1 into alpha of Ej1 to Ejk. So that means both left-hand side and right-hand side will be equal when applied to Ej1 to Ejk. And therefore, they're equal. Is this clear?
Yes.
Yes.
Okay. So what does that mean? That means that this EI1 star wedge EIK star, where I1 to Ik are strictly increasing in between 1 and n, this will be a basis of wedge K V star, right?
Yes.
Yes.
Okay. Well, I mean, it spans. You can see this. This is telling you that this spans. And to see that they're linearly independent, you just take a sum of these, which is 0. And then you apply it to a k-tuple of vectors ej1 to ejk. And you'll get that the coefficient of ej1 star wedge ejk star has to be 0, right?
Yes, yes.
Okay. So this will be linear independent. And so this will be a basis. Okay. So this tells me, therefore, what is the dimension of wedge K V star, right? It's just n choose k, right? Because I have to choose k numbers between 1 and n, right? Right? That is the dimension of this, the cardinality of this basis. It's just n choose k. Is this clear?
Yes, sir.
Okay, and it's 0 if k is bigger than n, right? Okay, because then if k is bigger than n, then basically in this ei1 star wedge eik star, some basis vector will be repeated twice, right? And so then this wedge product will become 0, because we know the wedge product is alternating on one forms, right? Right? Alpha sigma 1 wedge alpha sigma k, sine sigma alpha 1 wedge alpha k. So if any alpha is repeated twice, then this wedge product will become 0, right? Okay. So for k bigger than n, the wedge, the kth wedge is 0. All right. In particular, this tells me that the nth wedge product, the dimension is n choose n is just 1, and the basis of the nth wedge product is just e1 star wedge en star, right? Which is nothing but the determinant. Okay, so the nth wedge is just the scalar multiples of the determinant. Okay, is this all right?
Yes,
Yes,
it's
sir.
fine.
Okay, so now let's talk about pullback under pullback of tensors. So if T is a linear map from V to W, finite dimensional vector spaces, then we get a pullback map T star, which goes in the opposite direction from the kth tensor of W star to the kth tensor of V star. So if omega is a k tensor on W, then we define T star omega. This will be a k tensor on V. So this acting on k vectors V1 to Vk is defined to be omega acting on TV1 to TVK, right? Where V1 to Vk are vectors in V, and so TV1 to TVK are vectors in W, so omega can act on them, and that gives me a real number, okay? So this is the pullback of k tensors, and notice that the pullback of an alternating tensor will be an alternating tensor, right? So the pullback sends alternating tensors. Wedge k W star goes to wedge k V star. All right. Now, suppose T is a endomorphism of a vector space V of dimension n, and suppose E1 to En is a basis of V. So the determinant is just E1 star wedge En star. So what happens if I pull back the determinant? Well, I know that the nth wedge product is one-dimensional, spanned by the determinant. So therefore, the pullback of the determinant will be some constant c times the determinant. So what is this constant c? Well, what I can do is I evaluate both sides on the ordered basis E1 to En, right? So T star det of E1 to En is c times det of E1 to En. Now, det of E1 to En is just 1. So this right-hand side becomes C. And the left-hand side, I use the definition of pullback. T star det of E1 to En by definition is det of TE1 up to TEN, right? So I get that C is equal to the determinant of TE1 to TEN. But TE1 to TEN, this is just the columns of T with respect to the basis E1 to En, right? So this is nothing but just the determinant of T, right? So I get that this constant C is equal to determinant of T. So therefore, the pullback of the determinant, T star of det, is equal to determinant of T into det. Is this clear?
Yes, sir.
Yes, sir.
Okay, and therefore, by linearity, T star of any n form, omega, is just going to be det T into omega, right? Whenever omega is in wedge and V star, because omega is a scalar multiple of the determinant, and the determinant pulls back to determinant of T into the determinant. So any n form omega is going to pull back to determinant of T into omega. Is this
Right.
clear?
Yes, sir. Right.
Okay. So in fact, I mean, this gives an abstract definition of the determinant. So you see, wedge n v star, we know this is one-dimensional, right? So T star, this goes from wedge n v star to wedge n v star, right? So it's a linear map from a one-dimensional vector space to itself. So it must be multiplication by a scalar, right? Yes?
Yes, sir.
So this must be of the form omega maps to some constant c of t, depending on t, into omega, right? And so you can actually define the determinant abstractly in a purely abstract way, without any matrices, nothing, can define the determinant abstractly by saying that the determinant is this coefficient c of t. Right? Does this make sense?
Yes.
Then this will automatically give you that, you see, the determinant will automatically become multiplicative, because if I have two linear maps, S and T, right, what is S wedge T star of omega? So this is, so the pullback by S composed with T will be T star of S star of omega, right? And so S star of omega is what we're calling C of S into omega. And T star of this, I'll get C of T into C of S, right? Into omega. Yes?
Yes.
But on the other hand, this by definition is also equal to C of S composed with T into omega, right? So therefore, I get that C of S composed T is equal to CT into CS, right? So that means that the determinant is multiplicative. Is it clear? Yes?
Yes, sir.
Okay. So if you take this abstract definition of the determinant, then it's just one line proof that the determinant is multiplicative. Okay. All right. Okay. Now we can come back to orientation. Okay. So, so orientation is going to be the following. So first, let V1 to Vn and W1 to Wn, let these be two ordered bases of V. Okay. So then we say that they are equivalent, V1 to Vn is equivalent to W1 to Wn. If, so remember, when I have two ordered bases, that gives me a unique linear map T from V to V, an invertible linear map, which sends each Vi to Wi, right? So I'll say that these two ordered bases are equivalent if the determinant of T is positive. Okay. So this is clearly an equivalence relation, right? On ordered bases. And an orientation mu on V is an equivalence class of ordered bases. Okay. Is this clear?
Yes.
So this equivalence class is nothing but a connected component of the set of ordered bases, right? Like I was saying earlier. It's just a connected component of the set of ordered bases. Is that clear? Yeah.
Yes, sir.
Right. I mean, basically, this is saying that equivalence means that V1 to Vn and W1 to Wn, these are in the same GL plus orbit, right? These are in the same GL plus orbit. Yes. So therefore, they're in the same connected component, right? The two connected components are nothing but the two GL plus orbits, right? Is that clear? Yeah.
Yes.
Yes, yes, right.
Right. It's just the two GL plus orbits. So these are in the same GL plus. So the equivalence class is just the GL plus orbit. Okay. If you want to think of it that way, it's just a GL plus orbit. Okay. So, right. So on any finite dimensional vector space, the set of orientations is just a 2-point set. Okay, just a 2-point set. There are just two possible orientations on any finite dimensional vector space. Okay. And okay, so here's one thing to notice. If omega is a non-zero n form, a top degree alternating form, then it defines an orientation, mu sub omega. This will be the set of all ordered bases V1 to Vn, such that omega is positive on this ordered basis. So omega of V1 to Vn is positive. So, well, you have to check that this defines an equivalence class, right? So how do you do that? So suppose V1 to Vn and W1 to Wn are two ordered bases, and T is the unique linear map which sends Vi to Wi. Then what is omega of W1 to Wn? This is the same as omega of TV1 up to TVn. But by definition, this is the same as the pullback T star omega acting on V1 to Vn, right? But the pullback T star omega is nothing but determinant of T into omega, right? So this becomes determinant of T into omega of V1 to Vn, right? So now if I suppose that V1 to Vn belongs to this set mu omega, then that means omega of V1 to Vn is positive. And so therefore omega of W1 to Wn, this will be positive if and only if determinant T is positive, right? And that is if and only if V1 to Vn is equivalent to W1 to Wn, right? Yes?
Yes, sir.
Yes.
So this means that this mu omega, this is an equivalence class, right? This is an equivalence class. All right. Okay, so this is the orientation defined by a non-zero top degree form. Okay, any non-zero top degree form defines an orientation, mu sub omega. Okay, now we'll talk about something which is very important for us, which is what's called the volume form. So for the volume form, we need two things. We need an inner product on our finite dimensional vector space, and we need an orientation. So we have an oriented inner product space. So for example, you can think of Rn with its usual inner product and its usual orientation. The usual orientation is just the equivalence class of the standard ordered basis E1 up to En, all right? So Rn gives you an example of an oriented inner product space. So on this oriented inner product space, let's define dvol, the volume form of this oriented inner product space, to be E1 star wedge En star. Okay, so this is a top degree form where what is E1 to En? This is an orthonormal basis of V which belongs to the given orientation. So this is a positively oriented orthonormal basis. All right. Okay. So notice if I have any orthonormal basis, either it belongs to mu or it does not belong to mu. If it does not belong to mu, I can just interchange the first two basis vectors so that it belongs to mu. All right. So I can always find such a positively oriented orthonormal basis, right? Yes?
Yes, sir. Yes.
Okay. Now, what is the property of this? What are the properties of this d-vol? Well, I want to say that this definition is independent of the choice of positively oriented orthonormal basis, right? So now let me take another orthonormal basis, f1 to fn, all right, in which is also positively oriented, and let T be the linear map which sends EI to FI, all right? Now, because the EIs and the FIs both are orthonormal bases, T is an orthogonal linear map, and because E1 to En and F1 to Fn both belong to the same equivalence class, that means the determinant of T is positive. So therefore, T is an orthogonal linear map with a positive determinant. Therefore, the determinant of T is 1, right? Since its orthogonal determinant T is just plus or minus 1, but since the determinant is positive, it must be plus 1, all right? So now let me look at d-vol, my volume form applied to F1 to Fn. So this is going to be what? This is going to be, so F1, Fi's are T of EIs, right? So this is TE1 up to TEN. So therefore, by definition of the pullback, this is T star of d-vol applied to E1 to En, right? And what is T star of d-vol? We know this is determinant of T into d-vol, right? E1 to En, but determinant of T is 1. So therefore, this is just d-vol of E1 to En, but d-vol is E1 star wedge En star. So this acting on E1 to En is just 1, right? So therefore, d-vol of F1 to Fn is equal to 1, all right? So this means that this volume form has this very special property. It takes the value 1 acting on any positively oriented orthonormal basis of V. All right. It takes the value 1 acting on any positively oriented orthonormal basis of V. And in fact, this characterizes the volume form because, I mean, for example, if it takes the value 1 on this positively oriented orthonormal basis F1 to Fn, right, it takes the value 1, then what does that mean? That means that d-vol of F1 to Fn is the same as, it's equal to 1, and 1 is also equal to F1 star wedge Fn star applied to F1 to Fn, right? So these two are equal, both sides are equal to 1. But this means that my left-hand side d-vol and my right-hand side F1 star wedge Fn star, both of these are n forms which take the same value on the ordered basis F1 to Fn. Therefore, they have to be equal, right? If two n forms take the same value on an ordered basis, then they are equal, right? Yes?
Yes, sir.
Yes.
Okay. So therefore, d-vol has to equal F1 star wedge Fn star. Okay, so that means that this d-vol, which I defined as E1 star wedge En star, this is independent of the choice of positively oriented orthonormal basis of V. All right. Okay. So the volume form is actually the unique n form which takes the value 1 on every positively oriented orthonormal basis. All right. Is this clear?
Yes.
Yes.
Okay. So that's the volume form of an oriented inner product space. Okay. So we'll need this later when we talk about the divergence theorem and so on Riemannian manifolds. We'll need the volume form and Stokes theorem also. Yeah. Okay, so that ends what I wanted to say about alternating tensors. So now we want to slowly move to these concepts on manifolds. All right. So let me quickly just remind you of the definition of a smooth manifold. So now we're moving to doing calculus on manifolds. So a smooth manifold is a second countable Hausdorff space M together with a family of pairs ui comma phi I, such that the ui's form an open cover of M, and for every I, phi I is a homeomorphism from ui, which is an open subset of M, to its image phi of ui, which is an open subset of Rn. Okay. So these phi i's are called charts, and what we want is that what's called the change of charts should be a smooth map. So the change of charts is if two of these charts intersect, ui intersect uj, then I can look at phi j composed phi I inverse. So this goes from phi I of ui intersect uj, this is an open subset in Rn, to phi j of ui intersect uj. This is also an open subset of Rn. So I can, this is a map between open subsets of Rn, so I can talk about its smoothness. And what I require is that this is a C infinity diffeomorphism, okay, for all ij. So this map is called the change of charts. So, I mean, maybe I should just draw this picture for you. So here's ui, here's uj, and so I have phi I, I have phi j. So these are mapping to open subsets in Rn. And so the intersection maps to some subset here, and it maps to some subset here. Okay. And the change of charts is the map between these two shaded regions. This will be phi j composed with phi I inverse. Okay. So this ui union uj this is a subset of M. So let me call the images, say vi is phi I of ui. So this is an open subset in Rn. And this vj, this is phi j of uj. This is also an open subset of Rn. Abstractly, I can think of ui union uj, the union of these two open sets in M. This I can get as a quotient space, right? What am I doing? I'm taking vi by identify this points in this shaded area with points in this shaded area by this smooth map, right? Yes. So ui intersection, ui union uj, I can, this is homeomorphic to vi disjoint union vj quotiented by the equivalence relation. P is equivalent to phi j phi I inverse of P. Is this clear?
Yes, sir.
Right? So the point is, this is a smooth so relation induced by a smooth map. So relation given by a smooth map. So what that means is basically I'm taking open subsets Vi and Vj in Rn and I'm gluing them together smoothly, right? So similarly, the whole manifold M, I can write as a disjoint union of the Vi's. So these are open subsets in Rn modulo smooth gluing, right? Does this make sense? Okay, or gluing by smooth maps. Is it clear? Yes?
Yes.
Yes, sir.
So any manifold, a smooth manifold, I mean, if you want to think of it in a more concrete way, what you're doing is you're taking open subsets of Rn and you're gluing them together smoothly. That's what your smooth manifold is. Okay? You're taking open subsets of Rn and you're gluing them together smoothly. What are you gluing them together by? These change of charts map, phi j composed phi inverse, right? Okay. All right. So that is what a manifold is. So a manifold is given by gluing pieces of open subsets in Rn, gluing them together by smooth maps, by smooth diffeomorphisms. Okay. All right. So now we can talk about smooth functions on a smooth manifold. So we'll say that a function u on an open subset of my manifold M, taking values in R, is smooth if F composed phi I inverse. So when I compose with the inverse of a chart, that will give me a function from an open subset of Rn to R, right? So this this function I want to be smooth for all charts, which ui, which intersect the domain U of F, all right? So when I look in a chart, my function, which is defined on the manifold, locally it becomes a function on Rn. That function should be smooth, okay? And you can see that this is well defined, independent of the choice of chart, because if I choose a different chart, then I'll get another function, you know, F composed phi j inverse, which only differs from, so, I mean, what am I saying? So here, if I have, so I have on this intersection, I can use the chart. So how do I draw this? Okay, so suppose I have F, this is mapping to R. And then I have, say, a phi I. So this maps to some Vi. And then I have this map. This is F composed phi I inverse. Or I could go by phi j. And then I have a map on Vj, F composed phi j inverse. Right, but F composed phi j inverse is F composed phi I inverse composed with phi I composed with phi j inverse, right? And this is nothing but the change of charts map. This is a C infinity diffeomorphism. So therefore, this side, left-hand side, F composed phi j inverse is smooth if and only if F composed phi I inverse is smooth, right? Because they differ by composition with a C infinity diffeomorphism. Okay, So I can talk about smooth functions on my manifold. And similarly, I can talk about smooth maps between smooth manifolds. So, okay, instead of writing out the definition for you, let me just draw it here. So, if I have two manifolds, so say N and M, and then I'll say that a map F is smooth if for any point P here. So F I'll assume to be continuous, first of all. So then if I have P, I look at Q, which is F of P. Okay, so Q is F of P. F from M to N is continuous. And so I'll say it is smooth if the following holds. So first of all, I choose a chart near Q. Then by continuity of F, I can choose a chart near P, which maps into this chart near Q. And then I take the chart maps phi here and psi here. And then I get a map between open subsets of Rn and Rm. This will be psi F phi inverse. This is well defined. This map I want to be smooth. Then I'll say that F is smooth. Okay. All right. So we've got less than a minute here. So I think we should stop here. Right. So we've defined smooth manifolds. What are smooth functions on a manifold? And what are smooth maps on a manifold? All right. And so next time we'll start talking about the tangent spaces and vector fields and so on a manifold. Okay. So let's stop here today and I'll see you on Thursday. Okay.
Okay.
Okay. So see you Thursday.
So Thursday, 2 p.m., right? Same time?
Yeah, Thursday, 2 p.m. Yeah, usual 2 p.m.
Okay.
Okay. Okay. See you then. See you.
Sure. Okay.